Polarization. So let us define polarization before we do any comments and any explanation of the topic. So in order to understand polarization, you need to understand the nature of light first. So light was defined in different ways. It was called as a particle, it was called as a wave, and eventually we accepted the Maxwell's definition for light, which is it is the oscillation of electric and magnetic field. Electric and magnetic fields oscillate perpendicularly, and due to which the light propagates, which you can see on the diagram. And these oscillations are in pretty much all directions, but they would always be perpendicular to the direction of motion of light, or you can say to the direction of propagation of light. Now, out of all these oscillations, if we restrict those oscillations in only one direction, that would be called polarization. So it's just like we'll block each and every oscillation except for oscillation in a certain direction, then we say the light is now polarized. So we define it as restricting the oscillations of particles in one direction only. So check it out. This is your source of light, and this is the light that you get from that source. And in this one, as you can see, the particles, they are oscillating in all directions. And as the light propagates forward, as the light moves forward, we have placed something that we call polarizing filter in the path of the light. So what happens is all the oscillations are blocked except for the one that is parallel to the direction of the slits. So you can see the slits, or the slit in that case, is vertical. So all the oscillations are blocked except for the vertical oscillations. So we say the particles are now oscillating only vertically, and we have restricted the oscillations of particles only to vertical direction. This would now be called as polarized light. And like 99% of the questions that they ask in the exam, that is related to vertically polarized light. This one is vertically polarized light because you have only vertical oscillations in this one. And with this one here we have another example. So this is the source of light on the left side, on the extreme left side. So what do you see? The left side goes through the first polarizer, this one, and the light is vertically polarized, because after the first polarizer we are left with only the vertical oscillations. Forget about the second polarizer for now, we refer to the first one only. I'll explain the purpose of the second one also. All the oscillations in different directions, but once they pass through the first polarizer, because the polarizer was placed vertically, the slits were vertical, and it allows only the vertical oscillations, hence the light is vertically polarized. So what if I change the angle of the first polarizer? Let's place it horizontal. Let's go with 90. So you say, see, in that case the light is horizontally polarized. If I just rotate the 3D shape, you can see like this, and that's the top view. The slits are now vertical, only vertical oscillations would go through, and hence we'll say the light is, the slits are now placed horizontal, only horizontal oscillations would go through, and we say the light is horizontally polarized. Polarized in simple words mean it would be having oscillations in one direction only. And there you have in this one. Forget about the second, third and fourth slits. Just focus on the first one, the one on the extreme left side. So behind that slit, you were having oscillations in pretty much all directions. As the light passes through the first slit, that is called as polarizer, we are left with vertically polarized light because we have only vertical oscillations. So let's get back to the content, to the workbook. Yeah, that was the other one, as you can see. So what we see in this one is, once again, if you focus on the first slit, the very first one on the extreme left side, what you see is behind that you were having oscillations in pretty much all directions, but as the light passes through the first slit that we call polarizer, we are left with only vertical oscillations. So we say the light is polarized. Then we have the second, third and fourth. These are called analyzers, but we study that afterwards. But just focus on the first one. So once again, on the left side, what you have is the polarizer. As the light passes through it, it becomes vertically polarized because this Slits are placed vertically. Let's get back to the workbook now. Using the polarized filter or sheet. So in order to polarize the light, you have to use a certain kind of sheet, a certain kind of filter that is called Polaroid sheet or filter. So what do you see in this one? Once again, the same thing. You have a source of light. The source of light produces unpolarized light, and you have placed a polarizing filter that you can see, which is placed vertically. As the light passes through it, the horizontal oscillations are blocked. The blue ones, the horizontal oscillations are blocked, and only the vertical oscillations can pass through, and hence we say the light is polarized. And if we be more precise, we can say vertically polarized light. Now you see, if we place the slits vertically, vertical oscillation would pass through, horizontal ones would be blocked. So we can write a general sentence: oscillations parallel to axis of slit would pass through. And likewise, oscillations perpendicular to axis would be blocked. Then we have the next thing, types of polarization. So very easy one. We have two types of polarization, partial and full. So in partial polarization, vibrations are not restricted to one oscillation. And in full polarization, let us define full first. Vibrations are fully restricted to one oscillation. Vibrations or oscillations are restricted to one direction. And the example is when we get the vertically polarized light. So we have only a single direction of the oscillations, which is vertical, nothing other than that. And as you can see over here, we have represented two oscillations at the back, but as the light passes through the polarizing filter, we are left with only oscillations in one direction, which is the vertical. So this is fully polarized light. And in partial polarization, could be oscillations in more than one directions also. So oscillations are not restricted to one direction, right? Oscillations, you can write vibrations, are not restricted to one direction. Okay, then we have the next thing, Malus law. And with this one, it relates the intensity of the unpolarized light, or intensity of the light before and after the analyzer. Now, in order to make use of this law, we have to first polarize the light. And this law, for which we have a mathematical expression, this law works only if the light is polarized already. And then it would relate the intensity of the light. So let me take a look at the diagram. Step number 1, you have unpolarized light coming from a source of light. In step number 2, you place a polarizing filter that is placed vertically. The axis of the filter is vertical, hence all the oscillations are blocked. You can see this one oscillation blocked, this one 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 blocked. Only a single oscillation can pass through, which is the vertical one. These oscillations can pass through in step number 2. And as you reach here, the light is now vertically polarized. And this light would be having a certain intensity. This light would be having a certain intensity. Let's say the intensity of this light is I0. So I0 is the intensity of the polarized. So just forget about these ones. I0 is the intensity of the polarized light. Step number 4, we have another sheet, another polarizer, but in this case we call it analyzer because the light is polarized already in step number 2. So the second sheet would now be called as analyzer. These are the key terms, you have to use them as it is. So after the light, or I should say after the polarized light from step number 3 passes through this filter, its intensity would be changed. Previously the intensity was I0. This time the intensity would be, let's say, capital I. Then the law says that the new intensity and the old intensity are related, and they're related this way. Keep it in mind, I is the new intensity and I0 is the previous intensity. So this law says I equals to I0 cos square theta. So this is what the law says. The new intensity equals I0 times cos square theta. So what do we have up next? First of all, over here, I'm going to write down the expression once again. I equals to I0 times cos square theta. Now, what is the angle theta? Theta is the angle between the axis of slit and the direction of oscillation of light. Theta is the angle between the axis of slit and the direction of light. So let me write it over here. Theta, that's the angle between axis of slit and light. Let's check out these pointers. Natural light, for example sunlight, is unpolarized and it vibrates in all multitude of directions. However, this light can be polarized by applying a filter known as polarizer. Where do we have it on the diagram? The second one. Step 2. When a second filter is used in the path of now polarized light, it is called as analyzer. So let me show you the analyzer. Okay, so this is what we have. The sheet that you see on the left side is called as polarizer, because before that the light is not polarized, the oscillations are pretty much in all directions. So this sheet, this one over here, as the light passes through this one, only vertical oscillations are allowed to pass through, and hence this is called as polarizer. And the light that comes through the polarizer is now called as vertically polarized light. Now the second slit that you see, the second polarizer that you see now, it is called as analyzer. This one is called as analyzer. So how is the intensity of the light related before and after the analyzer? That is represented by the Malus law, which says I equals to I naught cos square theta. What is the angle theta? This one. Right now the angle theta is 0. And now the angle theta is 45. Now the angle theta is 90 degrees. Because the light was vertical, behind the analyzer, the light is vertical and the axis of the slit is horizontal. So the angle is 90 degrees. And once again in the middle, it is 45. So we can change the angle. And as we change the angle, the intensity of the light coming out of the analyzer would change. How would that change? How do we find it? Mathematically, numerically, we use the law I equals to I naught cos square theta. But keep it in your mind, when you use that law, you have to ensure that the light was already polarized. You cannot use that law for the first filter. And for this one, let me write down another thing. If intensity of unpolarized light is, let's say, 2I naught. Okay, just an assumed value. The intensity of the unpolarized light is 2I naught. After it passes through the polarizer, the first one, okay, when I say the word polarizer, I mean I'm referring to the first filter. The intensity would be I naught. So what does that mean? Well, it's just a fancy way. You can say a fancy way of saying that before the polarizer, whatever the intensity is or whatever the intensity was, after the polarizer, that intensity would be reduced to half. So I'm referring to the first sheet, the polarizer, not the analyzer. Then the question is, what's the relation for the intensity of the light before and after the analyzer? The answer is this one. So if you have to find the intensity before and after the analyzer, you can use this expression. So up next, on the next slide, what we have? Well, we have in the first step, we have unpolarized light that is coming directly from a source of light. In the second step, we have placed a polarizer that restricts all the oscillations and only the vertical oscillations are allowed to go through it. So in the third step, we have vertically polarized light. And the intensity of the vertically polarized light, you see, this is what we have written previously. If the intensity of the unpolarized light is I naught, if the intensity of the unpolarized light is I naught, then the intensity of the polarized light would be half of it, and thereby the intensity over here would be I naught divided by 2. Like in the previous case, in the example, I suppose the value of this one to be 2 times I naught. And after passing through the first polarizer, this is your first polarizer, the intensity was reduced to half. That's the same case. Instead of 2I naught, the intensity is I naught. After passing through the first polarizer, the intensity is reduced to half. What do you have after that? So in the fourth step, we have placed the analyzer. The second sheet is called analyzer. And the intensity after the analyzer would be changed depending on the angle between the light and the, and the axis of slit. So what is the direction of light? This one. What is the axis of slit? This one. What is the angle between these two? 0. So we can say theta equals to 0, and then this one. So once again, I'm referring to the steps. Step number 1, unpolarized light. Step number 2, we placed a polarizer. Step number 3, the light is now vertically polarized. Step number 4, we have the analyzer. Step number 5, the light passes through the analyzer. The intensity of this light would be found using the Malus law. But in this case, the angle theta is 0. Because whatever the direction of light is before the analyzer, the axis of this slit is also the same. So if you use the formula I equals to I naught cos square theta, then I is the new intensity. I naught is the intensity before the analyzer. Keep it in mind, this formula works only for the analyzer, not for this case, not for the polarizer. For the polarizer, the rule is intensity is always reduced to half. So we don't even need the formula for it. So I, the new intensity, equals to I naught cos square of 0, which is 1. So I equals to I naught. So what does that mean? Whatever the previous intensity was, the new intensity would remain same. So what was the previous intensity? It was I naught over 2, and the new intensity would also be I naught over 2. And why was the previous intensity, the intensity before the analyzer, I naught over 2? Because for the polarizer, the intensity was I naught. After the polarizer, the intensity always reduces to half. Then, so if the, now this one is the angle for the analyzer. Angle for the analyzer. What does that mean? The second polarizer. The second polarizer is your analyzer. So if that analyzer is placed at an angle of 0, which was placed over here, you see the angle between the light before the analyzer and the slit, axis of slit is 0. It's placed exactly the same way. So you get the maximum intensity. So if I show you from here, so this is the case that we are referring to. If the if the analyzer is placed like this, whatever the intensity of the light is here, the intensity after the analyzer would also be the same. Only if this analyzer is placed at 0 degrees, if the angle is 0 degrees. If you change the angle, you see the amplitude of the light changes, and hence the intensity would also change. What would be the new intensity? We can use the law to find the new intensity. And as I showed you over there, once I moved the analyzer to an angle of 90 degrees, the intensity was reduced to 0. So this is what we have over here. So as I move the analyzer to a 90 degree to the light behind it, the intensity was reduced to 0. So once again, if the analyzer is placed at 180 degrees, means just upside down. So the analyzer is flipped vertically. Still, the intensity would be maximum because all the light can pass through the slits. The light was vertical and the axis is also vertical. All the light can pass through it. And 270 once again means the analyzer is placed horizontally. No light can pass through. Intensity would be 0. 360 means you just completed one oscillation, one round trip of the analyzer. It was placed vertically, but you moved it all the way, make a circle of it, and it returns to the same point, but it's still vertical. The light behind the analyzer was vertical. It can pass easily. So intensity would be maximum once again. So 0 and the multiples of pi, the integral multiples of pi. So 0, pi, 2 pi, 3 pi, the integral multiples of pi. The intensity would be maximum. For what? For vertically polarized light after it passes through the analyzer.